Welcome back to Calculus 1. In this lecture, we're going to introduce the limit laws, which are the foundation of many topics within our course, Calculus 1. All right, let's think back to our previous lecture. We introduced basic ideas of limits, and we saw some examples with the numerical approach and then the graphical approach. Now, there's some drawbacks to those. The numerical approach required you plugging in typically many different values for x to observe a pattern in the y or function values. The graphical approach, well, that requires you to have the graph of the function or know it in advance. Sketching graphs or curve sketching, that's a long-term goal for us in a standard Calculus 1 course. So since typical functions in Calc 1 might be complicated, we might not know what their graphs look like currently. We don't want to rely necessarily on the graphical approach. So both of these approaches could be tedious and or difficult. So you might be thinking, is there a shortcut? And as it turns out, there's what's called the algebraic approach, which is arguably the most important of the three ways to understand limits for at least the beginning of Calculus 1. All three are important, but what we'll be getting to within the next lecture and kind of the next few, we'll be relying heavily on the algebraic approach. So let's go ahead and get into the foundation for the algebraic approach with two basic limits. The first one here involves a constant function, f of x equals c. All right, typically we're going to use c, or a lowercase c, to denote an arbitrary constant, just some number. All right, and what this is saying is as x approaches a of the constant function, c, what's happening to the y values or function values? Well, this is a constant function. All of the output or y values are constant, the same number, c. So as x approaches a, your function values are just equal to c. So we get this limit here, the limit as x approaches a of the constant function c equals c. Now let's visualize this graphically so that way it makes a little more sense instead of just stating this symbolically here with arbitrary constants a and c. Think of what the graph of a constant function y equals c looks like. Y equals a number, that's the equation for a horizontal line. So we'll just sketch some arbitrary horizontal line. Here I chose it to be above the x-axis. And what we think is what happens to the y or function values as x approaches a. Here, this is a two-sided limit, so we're going to approach a on the x-axis here from both sides. And you can see as you approach a from both the left and right simultaneously, kind of right above that along the horizontal line, your y values approach c, since all of the y or function values here are equal to c. All right, this one is, again, very basic. We're going to use this to build into things that are more complicated. Let's get to a second basic limit. Here, the function f of x for this limit equals x. All right, now this one is a little peculiar. We have the limit as x approaches a. So our x values are getting close to some number a. All right, and just think, as x approaches a, what does your function f of x approach? Well, as x approaches a, your function x also approaches a. So here, our limit as x approaches a for the function f of x equals x, that limit is a. Now, graphically, we can understand this similarly as above. Y equals x is not a horizontal line, but it's a diagonal line with slope 1. So if we were to sketch that graph, here we have the graph of y equals x. And we can see as we approach a from both sides, we're moving along that diagonal line, and we have our y values also approaching a. All right, this function, whatever your x value is, your y or function value is the same, since f of x equals x. When x is 1, y is 1. When x is 2, y is 2. When x is 3, y is 3. And when x is a, y equals a. All right, now these are not really the limit laws, but these are basic limits that we will start combining together to build more complicated functions. All right, let's get to what the limit laws are, which are the foundation for many topics within Calculus 1. We'll mention where this is going in a little bit. And before we state them, I'm going to put them all on the screen momentarily. What all these limit laws allow us to do is to split a given complicated limit or problem into a bunch of simpler limits or problems. This is a very useful mathematical problem-solving technique. Take a complicated problem and then split it into simpler problems. All right, and that's what the limit laws will basically allow us to do. So let's go ahead and state what the limit laws are. So we're going to have two functions here and two limits. Our two functions are f of x and g of x, and we have two limits as x approaches a of the function f, and the limit as x approaches a of g. We're going to assume both those limits exist. So in other words, as x approaches a, both the function values f of x and g of x approach each a single real number. All right, the first one is really two laws or rules in one. You could look at them separately as the sum or the difference, basically adding or subtracting two functions. And provided each individual limit exists, what this first limit law allows us to do, the sum or difference law, is take a sum or difference of functions in a single limit and split it up as a sum or difference of simpler limits. Now these rules, as we're applying them here, are only valid if each limit kind of all throughout this statement exists or is defined. All right, let's take a look at a second one. This is called the constant multiple rule or constant multiple law. Again, little c is denoting a constant. And it basically says if we have a function, f of x, and then multiply that function by a constant c, this limit law now allows us to take that constant c and then multiply it to the limit of the function. All right. Third one deals with a different way besides adding or subtracting to combine functions, multiplying. You can probably see how these basic operations, addition, subtraction, multiplication, division, start getting applied here. So if we have two functions, f of x and g of x, in which we multiply them and take a limit, well, we can just individually take the limit of each function, f and g, and then multiply those two limits together at the end, provided each limit exists. All right, you can probably take a guess what comes next. Sum and difference, addition, subtraction, product for multiplication. We have this quotient rule. And actually what I have stated here, make sure you see it in red. This looks like what you would think we'd be stating. We have a function here, f of x divided by g of x. So we've combined the two functions f and g by dividing or forming a quotient. Unfortunately, what's written on the screen here is mathematically incorrect. It's not just as simple as taking the limit of f and then dividing it by the limit of g. Why? Well, recall, limits, when they exist, they approach a real number. Anytime you deal with quotients or division, there's the possibility for division by 0. Now, this is basically correct, but we just have to give a kind of a small little technical statement to make it technically correct, just to avoid division by 0. So this is true, provided the limit of g of x, which is in the denominator, is not 0. That just basically allows us to avoid having to deal with division by 0 and making this undefined. All right, there's another rule which deals with taking a function raised to a power. So if we have a limit of f of x raised to a power n, where n is a positive integer, this power rule now allows us to equivalently evaluate the limit first of that function and then take an nth power of that limit. So we're going to see positive integers pop up a lot. All right, and then a related one, kind of related to powers. Think of radicals and roots can be written as rational powers. We have this root law dealing with an nth root here, which says if we have a limit of the nth root of a function, we can basically take first the limit of the function f of x inside, and then take the nth root of that. Now, this gets a little technical. I wanted to state the essence of what this root law allows you to do. But there's some technical parts here about the roots having to be defined. So recall when you have, for instance, a square root, or any even root for that matter, would be undefined with negative values inside the root or radical. So here, we just want to make sure that all roots are defined as real numbers for you to apply this. All right, so you might want to pause the video just to copy these down into your notes. We're going to use them for one quick basic example right now, but we're going to reference back to these within a few lectures. All right, so let's take a look at an example of how we would apply these limit laws. And let's take a look at what seems to be a simple limit. The limit as x approaches 1 for this function 4x squared minus 2x plus 1. Now, we're going to take the mathematical approach. We're going to try to build from one idea to the next in a logical fashion, a linear fashion. Use one idea to get the next, then the next, and so on. All right, so let's try to apply the limit laws. Here we have a complicated function. I would say this is actually not complicated, but to see how the limit laws are applied, let's consider this to be a complicated limit for a complicated function. All right, what we can apply first is a combination of the sum and difference rules or laws. So we have kind of three different parts or terms within our function, 4x squared, 2x, and 1. We can add and subtract three individual limits here. Now we should be checking that each individual limit exists, but they do. Take my word for it. All right, what we can do now to further simplify these is notice we have some constant multiples, 4 multiplying x squared and 2 multiplying x. So we can apply the constant multiple rule, bring the 4 in front of the limit, and bring the 2 in front of the limit as well. All right, and then the last one that we're going to apply, notice we have the limit of x squared. Recall we had earlier one of our basic limits, the function x involved in one of them. Here, x squared would be a power of that. So we can apply the power rule. All right, so we'll take the limit as x approaches 1 of x and then square that. That's breaking the limit as x approaches 1 of x squared down using the power rule. All right, and what we have now done is repeatedly broken a single complicated limit into several, 3 of them here, considerably simpler limits. And now we can rely upon our basic limits that we had earlier. Here we have limits involving the function x, and then the last one is a limit involving a constant function. So if we make use of those 2 basic limits from earlier, all these limits approach 1 by applying your 2 basic limit rules from before. All right, so at that point, we just kind of replace the individual limits with their values, which are all 1, and we have 4 times 1 squared minus 2 times 1 plus 1, which comes out to 3. So the limit here for this whole function as x approaches 1 is 3. All right, now that's how we mathematically apply and use the limit laws in practice. But this is not very convincing. Notice what happens if we just plug in x equals 1 from the beginning. If you take the function f of x as 4x squared minus 2x plus 1, just plug in x equals 1, skipping applying all these limit laws, you get the function value 3. So how do I explain this? Explaining that the limit laws are important, but you can see here, just plugging in makes it go so much quicker. What's the reason then that we would state in this course, Calculus 1, the limit laws? Because it looks like plugging in works, which it does here. Well, we need these limit laws for us to get to some really important basic rules or laws for the next fundamental topic after limits, which are derivatives. So I'll confess, we're not going to be using these limit laws for many examples. For instance, on homework questions, exam questions, there's not going to be much where I'll ask you to apply the limit laws. But we will come back and reference these when we get to derivatives. So we'll recall and write down, similarly, the limit laws with the new rules or laws for derivatives, whatever they are. All right. So let's give a follow-up here on what we were mentioning, something about plugging in. Now that we have kind of some ideas that can make this a little more easily understood. So the question we're going to pose is, when does plugging in work for evaluating limits? In other words, when we have a limit as x approaches a of a function f of x, when does that limit equal f of a? Just plugging in x equals a to the function. When is that valid? Now, it's not always true, but right now, for very simple functions, which typically are polynomials, just think polynomials are built out of constants and powers of x. So building, kind of from like a perspective of building from atoms, we start with our two basic limits, kind of at the beginning of this lecture, and then apply the limit laws to build up or construct a more complicated function, a polynomial. Again, polynomials are built out of constants and powers of x. All right, so the two cases when we can evaluate a limit by plugging in are when the functions involved are polynomials and rational functions. A rational function being a ratio of two polynomials here. P and Q denote polynomials. So here, P of x divided by Q of x would be a rational function. All right, the technicality there about plugging in is this plugging in or substitution rule only works if in the denominator, Q of a is not 0. Again, that eliminates the possibility for division by 0. All right, now these are actually going to be useful. We'll be relying on this a lot in the next few examples and topics. And again, they all follow, they are consequences of those limit laws. And that's typically what we'll be doing in a Calculus 1 course, developing some, I'll say, theoretical ideas, which might not be practical use, but then we'll use those ideas to get things that are more practical. Like here, these two basic rules are a little more practical than the limit laws. All right, let's take a look at a simple example. How we're going to evaluate this is typically we're not going to apply the limit laws to this anymore. You can to repeatedly break this down. But let's just plug in. We have here a polynomial function, so we can just plug in x as 2. And if you plug in x as 2 here, the limit comes out to equal p of 2, which, if you check, is 5. Right, and that's typically how we're going to apply the limit laws. We're going to use them in this form now, using these two results here about substituting or plugging in. Those will be a little bit more practical. All right, so let's get to the next part. After the limit laws, the next important thing is how we deal with limits with what are called indeterminate forms, which we did see one of those briefly before. This was within our first lecture, a limit as x approaches 0 of e to the x minus 1 divided by x. We saw plugging in gave 0 over 0. 0 over 0 is what we're going to define to be an indeterminate form. Let's go into detail with that here. So let's start with a simple example to motivate this. Let's say we're taking a look at the limit as x approaches 5 of the function x squared minus 7x plus 10 divided by x minus 5. All right, this one you can see if you plug in x equals 5, you get 0 in your denominator, 5 minus 5, and just check your numerator, plugging 5 in to x squared minus 7x plus 10, that also becomes 0. Just think 5 squared, 25, minus 7 times 5, that's 35. 25 minus 35, negative 10. Negative 10 plus 10, 0. So we get here 0 over 0, which is a very frequently encountered indeterminate form in the early phases of a standard Calculus 1 course. All right, so this is the simplest and most frequently encountered indeterminate form, but there are others. Notice we'd like to say a number divided by itself, like just think 2 divided by 2 is 1. Any number divided by itself is 1, with the exception of 0 divided by 0. 0 divided by 0, as we're going to see in the following examples, that indeterminate form, 0 over 0, actually could correspond with limits to any number. Hence why this is called indeterminate. It doesn't have a determined value like 2 divided by 2 equaling 1 would. All right, now there are other indeterminate forms besides 0 divided by 0. Here are the standard ones encountered throughout the calculus sequence. 0 divided by 0, infinity divided by infinity, infinity minus infinity, infinity times 0, 0 raised to the 0 power, 1 to the infinity power, and then infinity to the 0 power. Now, we're not going to see some of these for a while within our course, but I do want to kind of get all the standard indeterminate forms out of the way, since we're kind of going to detail with how we deal with limits with indeterminate forms within this lecture. All right, now that first one, it's going to be probably the most important early on in Calculus 1. We'll be seeing that a lot through the next few examples. And now we're left with this question. The kind of limit laws and results that we stated earlier in this lecture won't apply. So how can we evaluate limits with indeterminate forms? Well, we're going to use a simple idea. We're going to try rewriting the function into an equivalent function. And this is what I'll call using an algebraic trick. So the way we will rewrite a function is by doing something algebraically to the expression that basically is mathematically allowed. So we'll be relying on some ideas from algebra within the next few examples. And the motivating example here at the top of the page, just think for that function, x squared minus 7x plus 10 divided by x minus 5, algebraically, what could you do to that? Not much, but the numerator looks like something you'd be tempted to factor. So for this example, which we'll be getting to in the next part of this lecture, part 2, we're basically going to factor that numerator as our algebraic trick. So we'll rewrite this function by factoring it, and that will give us a way to evaluate the limit. All right, this concludes part 1. We're going to immediately pick up with part 2 with examples like this one here.